Hello everyone. Today we will continue section 16 on group action on a set. We will also derive Burnside's formula in this section. Remember that an action of a group capital G on a set capital X is a map star from G cross X to X such that Ex is equal to X for all X in X and G1 G2 of X is equal to G1 of G2X for all X in X and G1 G2 in G. Under these conditions, we say that X is a G set. Now let us consider an element small x in the set capital X and small g in the group capital G. If Gx is equal to X, we say that X is fixed under the action of the element small g in the group. Now, corresponding to a small g in capital G, the collection of all elements in X that are fixed under the action of small g is denoted with the xg, and corresponding to an element small x, the collection of all elements in G that leaves small x fixed is denoted with the gx. Now, in the previous class, we have seen the group action on a set capital X consisting of the vertices, sides, axes, diagonals, center and midpoints of the sides of a square denoted like this. Here again you can see the action of the dihedral group D4 on capital X, and here is the action table. Now let us calculate x suffix mu1. So what is mu1? It is the reflection of the square under the vertical axis. So you can see that the only elements of X that are left fixed under this action are S1 and S2, which means the sides, and the axis M1 and M2, the center C, and the midpoints P1 and P3. So if you look at the figure, you can identify these values. Also from the table, you can see the only elements of X that are fixed under this action. So you have X mu1 is equal to S1, S3, M1, M2, C, P1 and P3. Now using the table itself, you can find the other values. For example, what is X row naught? So you can see that all elements corresponding to the row naught are fixed, which means that X row naught is capital X itself. Now looking at the action table, it is easy to calculate these types of values. For example, you can see that X row 1 contains only one element C. Now if you don't have the action table and if you know the group action, then again you can calculate these types of values. For example, let us calculate X delta 1. So what is delta 1? It is the action defined by the flipping of the square with respect to the main diagonal. So you can see that the vertices 4 and 2 remain unchanged. Also the center and the diagonals D1 and D2 remain unchanged under this action. So you can see that X delta 1 contains the elements 4, 2, C and the diagonals D1 and D2. Now looking at the table, it is easy to verify the answer. So you can see that the elements 2, 4, D1, D2, C are left fixed under this action. Now let us calculate G1. What is G1? G1 is the collection of all elements in G that leaves 1 fixed. That means G1 contains the elements rho naught and delta 2. Now if you look at C, you can see that all the elements in the group leaves C fixed, which means that GC is D4 itself. Now can you find GM1? So without the table, it is possible to find the answer if you know the group operations. So do it as a homework. Now let us go to the next topic. Here let us consider the table once again. Here we are going to count the total number of pairs Gx with the Gx is equal to X. If you look at a row naught, you can see that row naught leaves all the elements of X fixed, which means that X row naught contains 17 elements. Now if you look at all such elements in capital X which are fixed by other elements of the group, you can see that there are a total number of 48 such elements which are left fixed by the group elements, which means that there are 48 elements or 48 pairs gx with the gx is equal to x. Now if you count the same number column wise, for example in the first column you can see that there are two elements that are left fixed by different group elements, which means that G1 contains only two elements. And if you count the same number column wise, we can see that that is also again 48, which means that summation over G modulus of xg is same as summation over x modulus of gx. Remember that summation of modulus of xg means that the number of pairs gx with the gx is equal to x which are added horizontally, and summation over x modulus of gx means that the number of pairs gx with the gx is equal to x which are added vertically. Here let us see a theorem, and let x be a G set, and you need to prove that G suffix small x is a subgroup for each x in X. You already know the definition and notation of Gx. Now in order to check whether a subset is a subgroup of a group, you need to show that it is closed under the same group operations, and you also need to provide the identity element and inverse element for each element in the set. So let x be an element in X, and let us consider Gx. If G1 and G2 are two elements in Gx, then you know that G1x is equal to x and G2x is equal to x, and you need to prove that G1 G2x is also equal to x. Now here if you start with the G1 G2x, you can see that that is same as G1 into G2x, since x is a G set, and that you can modify to G1x and which is equal to x. So G1 G2 is an element in Gx. There is no need to prove the associative property, since you already know that the elements are from G itself. Now you know that the identity element E is a member of Gx, since Ex is equal to x for every x in capital X. Now in order to prove the existence of inverse elements, let us choose an arbitrary G in Gx, and you just need to prove that G inverse x is equal to x. Now you know that G inverse x is same as G inverse into Gx, since Gx is equal to x, and you can modify it to get Ex and finally to x. Now what we have proved is that Gx is a subgroup of G, and we call it as the isotropy subgroup of small x. Now in this theorem you will learn how to partition capital X to different equivalence classes. For that you need an equivalence relation. Now you can see that two elements of capital X belong to the same equivalent class if you can move from one element to the other with the help of a group element, that is x1 tilde x2, if there is an element G in capital G such that Gx1 gives you x2. Since this is a simple proof, I am not going to explain that, so go through the proof and learn yourself. Now orbits are precisely the equivalent classes defined by the equivalence relation in the previous slide. So it is called the orbit in X under G. Now remember that if the orbit contains an element small x, we denote it with the Gx. For example, consider the table that we have seen already in this section. You can see that 1 is related to under the action of row 1, and 1 is related to 3 under the action of row 2, and 1 is related to 4 under the action of row 3. And you can see that no other elements are related to 1, which means that 1, 2, 3, 4 is an orbit. Now since this orbit contains the element 1, we denote it with G1. Now you can see that 2 is also a member of the same orbit, so you can call it G2 or G3 or G4. Similarly, you can see that S1 is related to S2 and S3 and S4 under the action of various elements in G, which means that you can have an orbit GS1. Now you can see that M1, M2, D1, D2. Now C is a single element orbit, and P1, P2, P3, P4 are orbits in X under capital G. Now let us have a look at the orbit GS1. If you note the notation of this orbit, you must see that this is different from G suffix S1, which is the collection of all elements G such that GS1 is equal to S1. The first one is a set, whereas the second one, that is G suffix S1, is a subgroup of G. Now in order to find a relation between GS1 and G suffix S1, let us have a look at the column of S1, that is the action of G on S1. We know that S1 is left fixed under the action of the group elements ρ0 and μ1, and we also know that this forms the subgroup G suffix S1. Now S1 is taken to S2 by the elements ρ1 and delta 1, and we can see that this forms a coset of GS1, and we call it ρ1 GS1 since it contains the element ρ1. Note that there is no problem calling the same coset by the name delta 1 GS1 since it contains the element delta 1. Now let's just look at the case of S1 taken to S3. Now you can see that rho 2 and mu2 are the corresponding group elements, and you have rho 2 GS1 is a coset of GS1. Now S1 is taken to S4 by the action of rho 3 and delta 2. So you have another coset which we denote with the rho 3 GS1. Thus we can see that corresponding to each element S1, S2, S3 and S4 in the orbit GS1, there is a left coset of G suffix S1. That is, the number of elements in the orbit Gx and the number of left cosets of G suffix x in G are same in this example. Now we can see that this is true in general, and we can see it as a theorem. So here is the theorem. Let X be a G set and small x be an element in capital X. We need to prove that the number of elements in the orbit Gx and the index of Gx in G are the same. So what is the index of Gx in G? It is the number of elements in the left cosets of Gx in G. Now when you need to prove that two sets have equal number of elements, you just need to prove that there is a map from the first set to the second set, and that map is 1, 1 and 1, 2. So here the first set is the set of elements in the orbit, and the second one is the collection of all left cosets of Gx in G. Now let us define a map psi from the first set Gx to the second set G over Gx like this. If x1 is an element in the orbit Gx, we know that there is an element G1 in G such that G1x is x1. So x1 is taken to the coset G1 Gx under psi. We need to prove that this map is well defined. Why? Because by the definition of psi, we know that if there is an element G2 in G such that G2 takes x2 x1, then by the definition of psi, x1 must be taken to G2 Gx. So in order to have a well defined map, we need to prove that these two cosets are the same. For that, we start with the element G1 inverse G2. If it acts on x, we can see that it is same as G1 inverse G2x, and that is same as G1 inverse x1 since G2x is x1. Now this is same as x. Thus we have seen that G1 inverse G2 acting on x gives x, means that G1 inverse G2 is an element in the group G suffix x. We can see that G1 into G1 inverse G2 is an element in the coset G1 Gx. That is, the element G2 is an element in the coset G1 Gx. Since G2 is an element in G1 Gx, which means that G1 Gx and G2 Gx are the same. So we proved that this map psi is well defined. Now it is enough to show that this map is 1 1 and on 2 in order to complete the proof. So we first prove that psi is 1 1. As the usual proof technique, we start with the psi of x1 equal to psi of x2. So psi of x1 and psi of x2 are left cosets of gx in G, and x1 and x2 are members of gx. Now by the definition of gx, there exists the group element g1 which takes x2 x1, and another element g2 which takes x2 x2, which means that by the definition of psi, you have psi of x1 is g1 gx and psi of x2 is g2 gx, and they are the same. So which means that g2 is an element of the coset g1 gx. Now this implies that g2 can be represented using g1 g, where G is an element in the group Gx. Now if you start with x2, you need to prove that x2 equal to x1. So if you start with x2, you can have x2 is equal to g2x, and this is same as g1 gx, since g2 is g1 g, and this is equal to g1 gx, which is equal to g1x, and that is equal to x1. So we started with the psi of x1 equal to psi of x2 and reached at proving that x2 is equal to x1, and hence psi is a 1 1 map. Now what remains is that we need to prove that psi is an onto map. For that, corresponding to an arbitrary coset g1 gx in G, we need to find the corresponding element in the orbit gx. So consider g1x and you call it x1. Then you can see that psi of x1 is taken to g1 gx, since psi of x1 is equal to g1 gx by the definition of psi itself. Now we have proved that psi is 1 1 and on 2, which means that the number of elements in the orbit and the number of left cosets of gx in G are the same. Finally, if G is finite, then the order of the collection of left cosets, that is order of G over Gx, is same as order of G over order of G suffix x. Thus we have the order of the orbit Gx is equal to order of G over order of the group Gx. Thus we can claim that order of the orbit Gx is a divisor of order of G, since you can write the previous equation as order of the group G suffix x is equal to order of G over order of the orbit Gx, and that must be an integer that we know. The final result that we want to discuss is the derivation of Burnside's formula. It says that if R is the number of orbits in X under G, then R times order of G is the sum over G order of Xg. Now in order to prove the Burnside's formula, we just need to start with the collection of all pairs Gx with the Gx is equal to X. Now if n is the number of such pairs, then for each small g in capital G, we know that there are xg pairs having G as the first member. That is, n is equal to summation over G order of xg. Now on the other hand, for each small x in capital X, we can have order of G suffix x pairs having x as the second member, which means that you can also write n as sigma over small x order of G suffix x. We already saw the same result in one of the previous example. Now since n is equal to sigma order of xg, which is equal to sigma order of G suffix x, in the previous theorem, if we apply the previous theorem, we know that since G is finite, we can have order of Gx replaced with the order of G over order of the orbit Gx. Now order of G is the number of elements in the group, and that is a constant. So you can rewrite this as order of G into sigma over x 1 over order of the orbit Gx. Now we calculate this sum in different orbits of capital X. That is, if O1, O2, O3, etc. are different orbits of capital X, we take the sum as summation over x in O1 1 over order of gx plus summation over x belongs to O2 where O2 is second orbit 1 over order of gx plus etc. Now if you look at the calculation of this sum on a particular orbit say O, then this is same as summation over x in O 1 over order of the orbit gx. Now order of the orbit gx means it is order of O, so you can rewrite this as summation over x in O 1 over order of O. Now how many times that you need to perform this sum? You can see that you need to perform order of times, that is the number of elements in the orbit. So this becomes order of O over order of O, which is equal to 1. So corresponding to each such a sum corresponding to an orbit, you will get the sum as 1. So the total sum becomes the total number of orbits, and hence you get this is equal to order of g times the number of orbits in X under G. Thus we have completed the proof of Burnside's formula, and there is a number of combinatorial problems waiting for us, and we will do it in the next class. Thank you.